Well, okay, thank you for coming to the last SNAPP seminar of this semester, and we'll be starting up again in the new year. So for the final talk of this semester, we have Andrew Stuart, who's at California Institute of Technology. Andrew Stuart's research interests are in applied and computational mathematics, and there's an interest in the question of how optimality combines with complex mechanistic models with data. He joined CalTech in 2016 as the Bren Professor of Computing and Mathematical Sciences, and has worked previously as a professor at the University of Warwick. Also was a faculty member at Stanford University and at Bath University. He did his PhD in Oxford and also did postdocs at Oxford and MIT. Andrew Stewart's got sort of an interest in the area of kind of uncertainty quantification, which is sort of through propagating randomness forwards and backwards through dynamical models. So I thought that'd be quite appropriate for the seminar series. So, okay, so thank you very much, Andrew.
Thank you, Neil. I'd like to thank the SNAPP organisers for the opportunity to give this talk, and I'd like to thank Neil in particular for his patience with my having to reschedule twice for COVID-related reasons. Thank you, appreciate that.
No problem, no problem. Great to have you here.
I'm going to talk about solving both optimization problems and sampling problems. In view of this being the applied probability audience, I'll concentrate most on the probabilistic and sampling perspective. And one of the primary motivations for this work is to solve problems without the use of derivatives. And I'll explain how that is done as we progress. The work is an overview and is collaborative with many people whose names you will see at the beginning in a list of collaborators, and as we go through the talk, when I will cite specific work. The slides are available, and all of the references and detailed history can be found by consulting them. So in this talk, what I'm going to do is, there are two aspects to the talk. One is solving filtering problems, and one is solving inverse problems. And in the first half of the talk, I will introduce the filtering problem, describe a perspective on it which uses mean field dynamics, which, although many of you will be familiar with filtering, this perspective may not be familiar to all of you. And then I'll use that mean field perspective to derive Ensemble Carmen methods and explain to you the sense in which they are appropriate for solving filtering problems, when they are useful. If I have time, I'll show an example in weather forecasting, but if not, it will be contained in the slides. And then in the second half of the talk, I will describe how the whole filtering methodology can be used to solve quite general inverse problems, making a connection with sequential Monte Carlo. I'll describe continuous time limits of the algorithms, which give great insight and lead to interesting mathematical structure. And if there's time, I'll show an example from an inverse problem in what's called electrical impedance tomography, which is a medical imaging methodology. There are three ideas that I would like you to learn about from this talk. The first one is the idea of Ensemble Carmen and how that is used or may be used to solve both optimization problems and sampling problems. The second main idea that I want to get across is the idea of using mean field models to derive the Ensemble Carmen methods. And I'll explain to you what I mean by this. But mean field models, in a word, are nonlinear Markov processes that depend on their own law. And by making particle approximations of them, one can derive a variety of different ensemble-based methods for optimization and sampling. And the third thing that I want the talk to emphasize and get across is the idea of solving optimization and sampling problems in a derivative-free fashion. And I will show you why that's important in many applications. There's alternative work on mean field approaches to both optimization and sampling using consensus. And for that work, I would point you to the work of Jose Carrillo and co-workers, some of which is referenced in 5 and 4, which you can get if you get the slides later. Okay, but I will not talk about these consensus-based approaches. I will concentrate on Ensemble Carmen-based approaches. I also wanted to say that I welcome questions. I know that Neil has volunteered to monitor the chat, so that's one way. but also feel free to interrupt at any time and ask a question, because you're a slightly different community than the one that I would normally talk on this topic to. I've tried to adapt the talk with that in mind, but questions will help your understanding, so please do interrupt. Neil, is there anything in the chat at the moment I should respond to?
No, not at the moment. I just shared the slides in the chat, but other than that, nothing else at the moment. Yeah.
Thank you. And the slides that Neil has just shared maybe don't have all of the references, because I've been updating them as I go, but I will make available the final version of the slides to Neil afterwards. There are many collaborators on this work listed here, and you will see them as we go through the talk. I wanted to particularly highlight in red here, Eduardo Calvello, who's a PhD student at CalTech, and Sebastian Reich, who is a professor at the University of Potsdam. The specific presentation that I'm going to give using mean field models to derive Ensemble Carmen methods comes from a paper that we are currently writing, Eduardo and Sebastian and myself, which is not yet complete. And as you can see, the work is joint with many other people listed here. Okay, so let me first discuss filtering and show you, define the filtering problem, with which most of you will probably be familiar, and thereby establish the notation that I'm going to use for it in this talk. I'm going to discuss hidden Markov model in the following form. The high-level notation that I will use throughout, dagger denotes the truth, a true signal that we're trying to uncover from data. V sub n denotes the state of the system, and n denotes discrete time. So the signal or state that we're interested in evolves according to this random dynamical system, in which psi is a typically nonlinear map, and psi n, for the sake of concreteness, I will assume to be a centered Gaussian throughout this talk. And the data model, we're going to, standard hidden Markov model, we're going to acquire data, which I will call yn plus 1 dagger, by observing the function lowercase h applied to the signal or state, vn plus 1 dagger, again with the addition of noise, and I will assume that that noise is also centered Gaussian. And just to be concrete, I will assume that the initial condition is random and is a possibly non-centered Gaussian with mean M0 and covariance C0. And a particular focus of this talk is the setting in which, I'll call this big model. Much of what we're doing is focused on settings in which Vn lives in a high dimensional space. Indeed, you could even think of it as being in a Banach space or a discretization of a Banach space. So we may have a lot of data, but typically the model is bigger than the data in terms of the dimension of the signal in comparison with the dimension of the data. And weather forecasting is a good example in which the dimension of the signal is about 1 billion, whereas the dimension of the data is in the millions. Okay, any questions on that panel? Because this is the notation I'm going to be using throughout, and everything will stem from this particular formulation. So if you do have questions, please ask.
I guess are the functions h and phi known to you?
Yes, so
in advance, yeah.
Yeah, so I'll assume that h and psi in this talk are known, and that also the covariances are known. Yeah. However, there are generalizations of everything I described to hierarchical models in which one can learn about these as part of the problem. But the ideas I want to get across, I will do in the context where psi, h, C0, sigma, and gamma are all known, and M0. Thank you. Okay, so the probabilistic picture here, I wrote, there were two equations on the previous slide, and just lifting up and looking at them from the perspective of the probabilities that they carry, the dynamics model, the equation for Vn plus 1 dagger, is Markovian and describes a update from measure mu n, where mu n is the signal at time n conditioned on all the observations up to time n. So uppercase yn is all of the observations y1 up to yn dagger. We are interested in the filtering problem. We're interested in the probability distribution mu n, and the signal is a Markov process, and therefore it maps linearly under a Markov kernel P from mu n into mu n plus 1 hat. And then to incorporate the data, that is yn plus 1 dagger, we apply Bayes' theorem to the predicted mu n plus 1 hat. A Bayes' theorem is an application of a mapping which I denote by L sub n. It's a nonlinear map on measures, because Bayes' theorem involves not only multiplication by the likelihood, but also normalization. So Ln, although I've written it in this way as if it might appear linear, Ln is a nonlinear map. So the filtering cycle can be viewed as a composition of a linear map P, describing the Markovian prediction, with a nonlinear map Ln describing Bayes' theorem. And as many of you know, the classic approach to this problem is the use of the particle filter. The true model, if I compose Bayes' theorem with Markovian prediction, gives a map that takes measure mu n to measure mu n plus 1 through application of the composition of Ln with P to mu n. The particle filter can be viewed as an approximation mu n super j of mu n, which is found by iterating the following map, where between Ln and P, one interposes a sampling operator. And Sj is the random map on measures. So Sj applied to pi is just found by drawing IID from pi and making a combination, a linear weighted combination of Diracs with equal weight. Okay, so this is the classic particle filter, and citations at the beginning of this section. And it converges. So I'm stating here a particular version of the convergence theorem, not for its historical significance, but for its clarity of presentation. It's in a paper of Rebshini and Van Handel. And in that paper, they use a metric, which is here we're talking about random probability measures because of the sampling process inherent in Sj. This is a metric on random probability measures, which reduces to total variation metric in the case of deterministic measures. And in that metric, one can show under some assumptions, for example, that H is bounded in the simple case, that the particle filter converges at rate 1 over root j, where j is the number of particles. So in other words, one obtains the Monte Carlo rate. So that looks good, but C of n being the number of steps in time, depends badly on dimension. And for high dimensional problems, where Vn dagger, the true signal, lives in a high dimensional space, and as I mentioned in weather forecasting, you should think of a billion dimensions. This method suffers from the well-known problem of weight collapse, namely that the application of Ln, which reweights this equally weighted sampling operation, will tend to weight just one particle with all of the mass, making this really quite an impractical method in high dimensional problems. Okay, so that's a summary of particle filtering and a specific issue that arises when one tries to apply it in high dimensions to serve as motivation for going beyond particle filters. So are there any questions about that brief summary? It also serves to establish my notation. Okay, so I'm now going to give sure there's no questions? Okay, I'm now going to give you a different perspective on filtering using the idea of mean field dynamics. The basic idea here is we introduced a measure which I called mu n, which was the filtering, the measure associated with the filtering distribution on the signal at time n, given all the data up to time n. The idea of this section is that we would like to write down a dynamical system which in law is equal to the filtering distribution. And necessarily in general, that dynamical system will be a mean field dynamical system, meaning that it will have to depend on its own law. Okay, so what you will see in this section are nonlinear Markov processes, which are equal in distribution to the filtering distribution. And this is an idea which goes back to Daum and co-workers in discrete time, and has been developed more recently in continuous time in papers of Krisan and Zhong, and this paper of Yang et al. And there's a yet more recent perspective on it due to Sebastian Reich, which you can also uncover from the references at the end of this paper. But the main idea I want you to bring into this section is that we're going to try and find a dynamical system, just to repeat, which is equal, whose law is equal to the filtering distribution. And that dynamical system will depend on its own law. So this is the idea that we combine two dynamical processes. One is prediction, based on predicting both the signal and the data. So I have hats here for the predicted signal and the predicted data. And what I want to do is create a dynamical system for Vn, whose law is mu n, where mu n is the filtering distribution that is given by the conditional distribution of the signal given the observations up to that time. All right, so I would like to make a dynamical system for Vn in which Vn in law is equal to the filtering distribution. And we do this by first predicting the state and predicting data. And then we try and find what I will refer to as a perfect transport map. So that is a map which will take the predicted signal and the predicted data, that's in here, and combine it with the observed data. And it will, this is a nu, not a v. This map will depend on a measure nu, which I will define for you in a moment. And I want to do this in such a way that Vn plus 1, encapsulated here will be a mapping from Vn, a random mapping from Vn to Vn plus 1. I want to do it in such a way that Vn is distributed according to the filtering distribution mu n, then Vn plus 1 will be distributed according to the filtering distribution mu n plus 1. Okay, that's what one would like. And it turns out there are multiple ways to do that in theory. And one can look at ideas, for example, from optimal transport. There's a lot of work in this area by Yusuf Marzouk at MIT and co-workers. But this is something which can, in principle, be done quite generally. The measure nu n plus 1 that appears in this mean field dynamical system is the distribution of the predicted signal, Vn plus 1 hat, jointly with the predicted data, Yn plus 1 hat. And it is possible to choose, in principle, a mapping TS, which depends on the predicted signal, predicted data, their distribution, Un plus 1, and the observed data, in such a way that if Vn is distributed according to the filtering distribution at time n, then Vn plus 1 will be distributed according to the filtering distribution at time n plus 1. So why am I telling you this? Well, in principle, if one knows TS, this leads to a filtering method, a particle-based filtering method, in which there is no collapse of particles. So to derive that method, assuming that one has this mapping TS, we're going to do the following. The mapping TS depends on the law of this predicted particle and the predicted data. And we're going to approximate that law by J predictions. So I'm going to run J copies of the predicted particle and J copies of the predicted data, uppercase J, and use them to compute an empirical approximation of the measure nu n plus 1, and I'll call that nu n plus 1j. And then one takes the given particles and the given predicted data, the empirical measure and the observed data, plug it into this map TS, which I have assured you exists. Indeed, it's non-unique. There are many possible such TS. Given one, one does this. And what you see here is a mapping from a collection of particles Vnj to a collection of particles Vn plus 1j. And in the large J limit, this approaches the mean field dynamical system on the previous slide. So if you let J go to infinity, this interacting particle system will approximate the system that you see here. And the system that you see here preserves the filtering distribution. So what we have on this slide is an interacting particle system, which in the large J limit recovers the filter, the particle filter, and the approximation that we have is an equal weights approximation. So in principle, this deals with the issue that makes the standard particle filter inappropriate in high dimensions, namely the issue of particle collapse. Because in this methodology, the mean field method, one approximates the measure nu n plus 1 by an equally weighted system of particles, and one also approximates mu n by an equally weighted system of Dirac measures at the particle positions. So in principle, this is a great idea because it beats the issue of particle weight collapse. So that sounds great, equal weights, no collapse, but the whole thing is premised on knowing the map TS. And in a sense, what I've done in just writing the map TS down and invoking use of it is just used its existence. I have not discussed how to compute it. And especially in these recursive filtering settings, it's very computationally prohibitive to compute TS in general, especially in the high dimensional setting, which motivates the work that I'm describing to you today. So the last few slides where I've talked about mean field dynamics, they serve to, on the one hand, demonstrate the value of the mean field perspective, namely to write down a dynamical system which depends on its own law and is equal to the filtering distribution, and to use that as the basis of a method through particle approximation of the mean field limit. That's one idea that I would like you to come away with from this part of the talk. But the second I'd like you to come away with is that it's not practical for high dimensional problems because of the last bullet here. The computation of the map TS is in general prohibitive. You can think of solving, for example, an optimal transport problem. So there will be, in this setting, a high dimensional linear programming problem to be solved to find TS. And that makes this method, as I've described it, prohibitive. However, it's going to serve as motivation for a method that does work. And I would therefore, I'd like to take this opportunity to ask you again if there are any questions and things I can clarify about the method that I'm describing here.
There aren't any questions in the chat, but I had a couple of questions anyway. So I guess usually what people do is do some sort of importance sampling or something like that. That's sort of what like this sort of sequential Monte Carlo would do. And then what happens there is you're basically throwing away, trying to keep some particles alive. And here you just say you don't need that at all, basically. You can just keep J equally important particles alive at all times, and they're going to follow the correct distribution.
That's right.
Is that correct?
That's correct. That's the idea, yes. And I should say that even with importance sampling, so for example, if you follow Doucet's idea of the optimal particle filter, it still suffers from collapse in high dimensions. It's better than the basic method that I've described, but still particle collapse is an issue. In principle, the method I describe here gets around particle collapse, but it's not really yet practical because of the computation of TS being prohibitive.
Okay. And there aren't any other issues with TS, for example, you need continuity things there as well, I guess, as the measures get close to each other, you need that third component there to be nice and well behaved, I suppose, in the mean field limit.
Yes, you mean you want the map TS to have continuity? Yes, indeed you do. So you will want to, if this were a method that were practical, you would want to look for TS which had smoothness properties. But what I'm going to do is not compute with TS, but do something slightly simpler, which I will describe on the next slide. But it will be conceptually very similar to the ideas that are in the last few slides and which you have just explained and summarized really well. Thank you, Neil. Okay, any other questions on this? All right, so I'm going to describe the Ensemble Carmen method from this mean field perspective. So of course, Carmen's original paper is from the early 1960s. The Ensemble Carmen idea comes from the mid-90s and is due to a Norwegian geoscientist, Evensen. And the link to transport and the mean field perspective that we're giving here comes from the paper of Reich from 2013, which I mentioned earlier. So the idea here is that I'm going to approximate the map TS by a map TS that will be exact in the case where nu n plus 1, which was the predictive distribution of the jointly of the state and the data. The method I'm going to describe now is a mean field method, which would be exact if nu n plus 1 were Gaussian. Okay, so this is a TS. I'm writing down an explicit transport map TS, but it would only be exact in the case where nu n plus 1 is Gaussian. And here is the map TS, highlighted here. So what form does it have? To compute, given the predicted particle Vn plus 1 hat, one adds a Carmen gain, whose form I'm going to come back to in a moment, because this Carmen gain depends on its own law, applied to the difference between the observed data, yn plus 1 dagger, and the predicted data, yn plus 1 hat. And the Carmen gain is computed from two covariances. Those are covariances under the distribution of joint distribution of the predicted particle Vn plus 1 hat and the predicted data yn plus 1 hat. So these data covariance and the cross covariance from the data to the signal are computed under the distribution of the predicted particle and the predicted data, their joint distribution. Okay, so this is a mean field model because this Carmen gain depends on the law of Vn plus 1 hat, yn plus 1 hat. Okay, and it is of the form TS that I wrote before. It depends on the predicted particle for the state, depends on the predicted data, yn plus 1 hat, and it depends on the observed data, yn plus 1 hat, and importantly, as a mean field model, it depends on its own law through this Carmen gain, which is computed using expectations under the distribution of the predicted particle and the predicted data. All right, but if this were if we were Gaussian, this would be exact, and I'll come back to the implications of that in a moment. But the thing is, you can use this method even if nu n plus 1 is not Gaussian, and that is the essence of the Ensemble Carmen method. We take what you see on this panel here, the predicted and then the transport, and we'll just apply a particle approximation. So on the next slide, you see the same thing where the expectation with respect to nu is now computed using an empirical expectation of the joint distribution of the predicted signal and the predicted data. And this is now implementable. It involves computation of empirical covariances and therefore empirical means of the predicted data and the predicted signal. And those are used to compute a Carmen gain, which depends on the law of the particles, the empirical law of the particles. And then one has an update in very standard Carmen form, where you take the predicted particle and you add an innovation, which is based on comparing the observed data with the predicted data, and a Carmen gain, which is computed empirically from the system of interacting particles. And once again, this leads to an equal weights approximation of the distribution, of the filtering distribution, mu n. But remember that this transport map is only exact if the problem is Gaussian. So are there any questions about the method?
If I may, actually.
Please.
So, I wrote something in chat, but now I sort of realize I'm barking up the wrong tree there. So these equations are essentially saying that you have this sort of large joint Gaussian distribution over multiple time periods. And what you're doing is looking at the marginal Gaussian conditional distribution at time n plus 1, given this other information that you can observe.
That's right, yes.
Right.
So this, what you see here in this transport would be, it's exactly, well, in distribution, this would recover the Carmen filter. If everything were, if psi and h were linear and initially was Gaussian, then everything would be Gaussian. And that's exactly, one would recover something which in distribution was the same as the Carmen filter. But the method can be applied empirically without requiring the distribution to be Gaussian. There's a separate question as to what it then approximates, but it can be applied, and that is what the method is. So one just applies the method, computing the Gaussian, computing as if one were Gaussian, even though one is not in general. Did I answer the right question, Shane?
You did. Thank you very much, Andrew. I'm starting to sort of get the shape now. So with the notion that you're working somewhat with the concepts of Gaussians, it also sort of makes me think that as long as sort of two moments are sufficient to sort of reasonably capture the distributions you're dealing with, it may not be too bad. But if you're dealing with distributions that maybe have poor tail behavior or something, then this may not be such a good idea. But perhaps I should wait and see where you're going.
No, that's exactly right. So I think that the reason for the success of the method, as empirically perceived in the geosciences, is precisely because many of those problems are close to being Gaussian, because they're fairly well informed by data, and there's some kind of Bernstein von Mises effect. That means that although the problem is nonlinear, the distributions are close to Gaussian. So firstly, that's motivation for why I think the methods work well in practice many times, but it's very easy to construct examples where this method fails. You could do it via the tails or through multimodal distributions in a fairly straightforward way. So you're spot on. Thank you. Any other questions about this method? Okay, so there is following on from the discussions we just had, there's a paper of Legland and Coworkers more than 10 years ago, which shows convergence of this method with a slightly different metric from the one I described earlier, the work of Repshini and Van Handel for the particle filter. This uses a different class of test functions with locally Lipschitz properties and polynomial growth, as opposed to functions bounded in L infinity, which is what I quoted earlier. But essentially one obtains the Monte Carlo rate. And so what this shows is that, as just discussed with Shane, the method is a particle approximation of the Carmen filter and recovers the Carmen filter in the large J limit. However, it also in this paper, it is demonstrated that in general, the large J limit in the nonlinear case is not equal to the filtering distribution. And so if this method is to be useful, then it will have to be useful when the distribution one is computing is close to Gaussian. And papers exploring that from a rigorous point of view beyond this paper of Legland do not yet exist. So I think there's a lot of scope for mathematical analysis in this area. Okay, because I'm mindful of wanting to describe to you how this method applies to inverse problems, I'm going to skip the little section on application of this method to weather forecasting. But those of you who are interested, you can have access to the slides and follow this up. And you will see that a real world example from the German weather forecasting service, which shows the advantage of the Ensemble Carmen method in making predictions of the real weather in comparison with 3D VAR, which is a form of averaged extended Carmen filter, with the Carmen gain computed in an average sense. Okay, but I won't, unless there's time at the end, I won't dwell on that example. What I want to do is move into the second half of the talk, which is to show how this methodology may be used to approach general inverse problems. So there's a lot of background here on the solution of inverse problems in general. And the specific idea of using ensemble methods for inverse problems really arose in the oil industry. And these two papers of Chen and Oliver and Emmerich and Reynolds are the historical progenitors of the idea. The paper of Reich, which I've mentioned before, also touches on this solution of inverse problems in the general framework I'm going to describe here. And in this paper of Iglesias and myself and Cody Law, we established the method as a general optimization approach for inverse problems. As with we just discussed with the work of Legland, in general, these methods will not produce the solution of the true Bayesian inverse problem unless one is in the linear Gaussian setting, and that is analyzed in this paper of Oliver Ernst and co-workers. Right, so there are limitations on this methodology, and one should think of problems which are close to Gaussian as being the appropriate place in which to use these methods. And furthermore, problems in high dimension, where the state that one is trying to determine is a high dimensional vector or even a function. So the general inverse problems I want to look at have this form here. One is trying to recover U, which you could think of as high dimensional or an element of a Banach space, from data Y, which is found by application of a nonlinear map G to U, and then the addition of Gaussian centered noise, eta, with covariance gamma. And throughout this part of the talk, I'm going to use single bar to denote the Euclidean norm. I'll do everything in finite dimensions, though you can work in Hilbert space, but we'll do everything in Euclidean norm. And this will denote what I call the covariance weighted Euclidean norm. And that's found by applying a to the minus a half to the quantity in question, and then applying the Euclidean norm. So this this is the norm defined by the quadratic form that arises naturally in Gaussian measures with covariance A. So this makes sense when A is positive definite symmetric, which is what is assumed. Okay, then the Bayesian solution of the inverse problem is as follows. One puts a prior distribution on U, and then conditions on the data Y, where Y solves this equation, with the assumptions that U and eta are independent a priori. And then the posterior distribution is found by reweighting the prior according to this likelihood, which is computed from this weighted least squares function, y minus g of u squared. The weighting by gamma being the weighting that is described here. So gamma is positive definite symmetric, and we can therefore use this definition. All right, so in the Bayesian approach to the inverse problem, the objective is to sample the measure mu, which is a reweighted version of the prior. Reweighted intuitively so that high probability with respect to the prior reference is obtained in the posterior measure when this objective function is small, so that the data is well matched. Okay, any questions on that formulation? Because I'm now going to link this back to filtering using the standard sequential Monte Carlo idea. All right, so the idea of sequential Monte Carlo, and this is the very influential paper of Del Moral, Jezra, and Doucet from 2006, which shows, amongst other things, that the inverse problem that I've just described can be reformulated using filtering. And the idea is to introduce a sequence of measures mu n, which, as one steps through n, make a homotopy, if you like, from mu0, the prior, to the posterior mu. And that is done by weighting the likelihood by n, lowercase nh, assuming the uppercase nh is 1, and then noting that from the sequence of measures mu n, mu uppercase n is equal to the desired posterior distribution. And also noticing that mu n plus 1 is computed from mu n by reweighting by e to the minus h phi. And h is small, and so consequently this reweighting is much more benign than reweighting by e to the minus phi itself, because h is small. And the small increments that arise from reweighting by something close to the identity make it possible to morph the prior distribution mu0 into the posterior distribution mu sub uppercase n through a sequence of measures mu n. And then one can ask, can we write down a random, a hidden Markov model, which at each n is given, has law given by mu n? That's the basic idea, which amongst other things is highlighted in this paper of Del Moral. And actually based on earlier work of Chopin and Radford Neal. So the basic idea is that one can write down a stochastic dynamical system that is, whose filtering distribution is equal in law to the measure mu n, the sequence of measures mu n, mu lowercase n that I wrote here. And that, excuse me, that stochastic dynamical system is very simple. The signal itself evolves with trivial dynamics, and the data evolves according to the observation map G with noise, which instead of having variance gamma has variance, large variance, scaled by gamma scaled by 1 over h. And remember, h is small. and the product of H and uppercase N is 1. And so this is a model in which the noise is large, which makes it relatively easy to apply Bayes' theorem and makes this a practical method, at least in low dimensions. So the key point is that this dynamical system has the property that Vn dagger conditioned on the observations up to time n is given by the measure mu n on the previous page. And since mu uppercase n is equal to the posterior distribution, if we solve this, the filtering problem associated with this dynamical system, we will compute at time uppercase n the desired distribution. So that's just the idea of sequential Monte Carlo. But we may now apply the ensemble method to solve this problem. And what I want to do is describe a continuous time limit of the ensemble method and connect it with gradient descent to try and show you why it is that the ensemble method works well. So the continuous time limit, I think, is best thought of not as an algorithm, but as a way of understanding the use of ensemble methods applied to the solution of inverse problems. So if you take if you apply the Ensemble Carmen methodology to the dynamical system described by the sequential Monte Carlo method, you get a system of interacting stochastic differential equations. They're mean field stochastic differential equations, sometimes known as McKean diffusions. So the U itself depends on a U prime, which is distributed according to the law of U. All right, so U prime is just a dummy variable distributed according to the law of U itself. So this is a stochastic differential equation that depends on its own law. So if I write down its Fokker-Planck equation, the Fokker-Planck equation is nonlinear because the differential equation right-hand side involves expectations under the law of U itself. Okay, so this has a nonlinear Fokker-Planck equation, and it has some interesting properties. So this is gamma prime here. We'll take two values in what I'm about to describe. If I choose gamma prime equal to gamma, and if I look at the case where G is linear, remember we've discussed that this methodology is somehow exact. The transport methodology is exact in the case where we have linear Gaussian problems. In this setting where gamma prime is gamma and G is linear, if you integrate this system of differential equations, which even when G is linear have a nonlinear Fokker-Planck equation, which is also non-local, and the solution of that Fokker-Planck equation at time 1 is equal to the solution of the inverse problem, the Bayesian inverse problem. Is there a question? No. Okay, so this nonlinear Fokker-Planck equation at time 1 will solve the inverse problem in the linear case. And secondly, if I look at the case gamma prime equals 0, this gives an optimization algorithm, which I'll refer to as Ensemble Carmen inversion. And on the next slide, I'm going to describe the structure of that optimization algorithm. So I'm going to set gamma prime equal to 0 and look at the resulting mean field dynamical system. And I'm going to look at it under a linear approximation where I replace G of U prime, where U prime is distributed according to the law of U, minus G bar, which is the average of G of U prime under the law of U. I'm going to linearize it in this way. And if you make that linearization and substitute into the mean field dynamical system that I've just shown you, what you get is gradient descent for phi 0. Phi 0 is the least squares function associated with the inverse problem. So phi 0 is y minus G of U squared in the covariance weighted Euclidean norm. But this is not any old gradient descent, and understanding what I'm about to tell you now is key to understanding why ensemble methods are so effective. It's a gradient descent that has been preconditioned by a matrix C, and the matrix C depends on the law of U. And that dependence, I'm going to show you as we generalize beyond this slide, gives rise to algorithms which have very desirable convergence properties. It is possible to analyze the algorithm that you see here, but I'm going to go beyond it and look at a stochastic version of this. But what I would like you to take away from this slide is that the Ensemble Carmen method applied to the solution of inverse problems is essentially approximating gradient descent, but doing so with a preconditioner which is computed based on the empirical covariance of the mean field model, or when one uses particles, of the empirical approximation of the mean field model. So once we have gradient descent, we can also look at sampling and go to a Langevin picture. So what I'm doing here is taking the optimization perspective, that's the first part of this mean field dynamical system, and I'm going to put it in a heat bath. And I do that in a specific way. So this is a damping, which comes from the prior distribution, and this is noise. And these are used with a weighting that is weighted on the basis of the empirical, well, here I'm doing the mean field limit. In practice, one would use a particle approximation. So the C of mu is given by the covariance of U under its own law. So this is a stochastic differential equation. Again, even when G is linear, or regardless of G, the Fokker-Planck equation is nonlinear and non-local. It's nonlinear because of the dependence of this stochastic differential equation on its own law, mu. All right, so if you make the same linearization ansatz that I showed before, you get a Langevin equation where the Langevin equation is preconditioned by a matrix which depends on its own law, so both the gradient term and the noise. Nonetheless, this equation has the invariant measure e to the minus phi, where phi here is the regularized least squares function, with the regularization reflecting an assumed Gaussian prior distribution on the unknown parameter u. And now this leads to the key point that I would like to get across about why ensemble methods work well. This slide is a little bit technical, but I'll leave it there for those of you who might be interested. There's a gradient structure for the Fokker-Planck equation as well, which builds on famous work of Otto a couple of decades ago, which showed how a number of nonlinear parabolic equations had a non-trivial gradient structure in the space of probability measures. And using a generalization of the natural Wasserstein metric, which arrives in Otto's work, to this Kalman setting. And you can find this generalization in the book of Kotter and Reich. And this paper shows the gradient structure of the nonlinear Fokker-Planck equation. And using that, one can prove the following result, which applies in the linear case, which, and this is really remarkable. It's only in the linear case, but what you see here has implications beyond the linear case for many problems which are close to Gaussian. But in the linear case, provably, this methodology converges at a universal rate, e to the minus t, which is independent of the problem that you are solving. So the use of the interacting particle system leads to convergence rate that does not depend on the problem you are solving. And if you take yourself back to your knowledge of steepest descents, you will know that steepest descent methods converge at a rate that, in general, depends on the condition number of the matrix defining the quadratic form that one is optimizing. The key point here is that dependence on the condition number of the problem disappears, and the rate of convergence is independent of the problem being solved. So that's a really remarkable property and is key to understanding why the ensemble method works well. I'm just going to show you very quickly an example of the ensemble method. And it's a good example of why we would like to solve, but how it can be used for inverse problems which are involve a forward model G, which is not differentiable. You won't take in all of this PDE stuff. Let me just say that electrical impedance tomography it's used in medical imaging and also subsurface imaging. You inject current on the boundary of an object and measure the voltages that result. So you have an Ohm's law relating current to voltage, and the Ohm's law has a resistivity matrix that depends on the interior properties of the medium. And then using that, there's an inverse problem to determine the interior properties of the medium. And the resistivity matrix is defined through solution of a complicated PDE, which we see written here. When you do medical imaging, you're often interested in things like good and bad tissue. So here, blue is good tissue, red is bad tissue. And so the inverse problem here is for piecewise constant function with unknown interfaces. And we solve that by a level set method. So that is the ensemble. And here you see ensemble means. And we're trying to solve this problem here. We work with functions here whose ensemble mean is being shown. And thresholding the function that you see here gives rise to our estimate of the solution of the inverse problem. Thresholding is a non-differentiable operation. So the overall forward map that we use here is non-smooth. And you see that at the end of 5 iterations, we've recovered a good approximation of the true conductivity of the interior that defined this problem. Okay, thank you. I should stop here. I'm grateful to you for listening and welcome to answer questions.
Okay, super. Thank you very much. Quickly give a quick clap or e-clap, as it were.
Thank you.
Thank you. Are there any questions from the audience?
I'm curious about the. Oh, sorry. Go ahead, Jane.
No, Shane, you can go first.
Okay. Well, thank you. The preconditioning looks very much like a sort of a Newton system of equations where one multiplies by the inverse of the second derivative matrix, except that you're not taking into account the map itself. It's really in the initial variables. Is there is that where is that really what's driving the main result, that this leads to these sort of beautiful complexity results, that somehow you're recovering much of the nonlinear dynamics there?
Yeah, that's a good connection. So there are methods based on ensemble which do you can have an interacting system of particles which approximate the Newton method. That's not quite what's going on here. Okay. It's closer to something called a Levenberg-Marquardt method. But the general concept that you can use particles to approximate derivatives and thereby approximate a whole range of different optimization methods or sampling methods that stem from those optimization methods. That's quite a general concept beyond what has happened here. What's really happening here is that if you look at this problem here, if phi is quadratic, if phi is quadratic, the measure of interest is e to the minus phi. The best possible preconditioner you could use is the covariance of the posterior distribution, because if you change coordinates using the covariance, you sphericalize the Gaussian measure. So what this method is doing is, and this is a commonly used in adaptive MCMC, it's essentially learning the covariance of the distribution and using that to precondition or change coordinates in such a way that everything is sphericalized, and therefore you get these rates of convergence that are independent of the problem. So it's automating something which is there's work of Achade and later work of Gareth Roberts, which shows adaptive MCMC using learning of the mean and the covariance along the way. So I think that's the closest analogy.
Thank you.
Thanks.
So I would like to ask, like, in implementations of this algorithm, so is the sampling part the most computationally intensive part, that you're trying to get these target distributions at each level, and also you're not able to, I guess, simulate these continuous time processes. You have to do some approximation of these continuous processes. So there's like error introduced in the process. So are there any like tuning, or is there a good choice of like how to do discretization in general?
Yes, thank you. That's really good questions. So there are two aspects to that discretization. One is, let me just go back to the particle system. There are two aspects to discretization. One is time discretization, and the other is the number of particles. So let me first discuss the number of particles. The number of particles affects how quickly one is able to evaluate these empirical covariances in the data space and the cross covariance from the data space to the signal space. And the success of the method comes in settings where low rank approximations of high dimensional covariances are effective. And one of the reasons that low rank approximations, well, let me just say, in general, low rank approximation may not work. Okay, so you can write down problems in which a low rank approximation of the covariance will not be sufficient, and then these particle methods will not behave well. However, I'd like to show you the weather forecasting example because that addresses exactly this issue. What makes weather forecasting difficult? There are two things, one of which is covered here. The two things that make weather forecasting difficult are the butterfly effect, namely that the system is chaotic, and the other one is that the model is imperfect. The use of data can be used to deal with both of those issues. And this figure shows how the butterfly effect, which is present in the top figure, is solved by using data. And the reason, and I want to link this to the low rank covariance approximations, this is what you see here is a high dimensional dynamical system. It's a partial differential equation. It's actually an infinite dimensional dynamical system, but the number of unstable modes is on the order of 50. So if you think that when you discretize this problem to get a high dimensional filtering problem, there is a very high dimensional filtering problem, but the instability in the system is of dimension around 50. And as a consequence of that, it's possible to make low rank approximations that based on particles of these covariances, which are accurate. But coming back to your question, that needs tuning, and understanding how many particles you can get away with is related to understanding, in the case of weather forecasting, the instability present in the system at the time that you're integrating. So there's a real need for analysis to try and understand what I've just given you a hand-waving answer to, namely, how to choose the number of particles as a function of the problem itself to get a good low rank approximation. So very much an art at the moment, which is crying out for more mathematization. Regarding time stepping, I would say that the continuous time stuff I described at the end is really more for understanding. The mathematics is more beautiful, and it's easier to analyze things in continuous time for the type of analysis I like. But in practice, it's best to use, as with steepest descent, it's best to use large time steps or learning rates, which are adapted to the solution and adapt with n. And there are some heuristics about that, but again, more theory is needed. Thank you. That was a really good question.
Thank you.
Super. I'll